Okay, so after a long pause, we are back to condensed matter physics. Actually, the pause was in an fortuitous point. It was in a point where we finished X-ray scattering from a lattice. And what we are going to do in the next few lectures will be, first of all, to see what is the energy actually that keeps this lattice together. And after that, we'll talk about acoustic waves in these lattices. Okay, so basically, what is the energy that forces these lattices to, so that the atoms will be in the lattice points? Well, it depends on the lattice. If you remember, we said that we have different types of bonds between the atoms. We had molecular bonds, ionic bonds, covalent bonds, and so on. Okay, so for the molecular and ionic bonds, we will do explicit calculations. For actually the covalent bonds and the metallic bonds, the game is much more complicated, and we won't do anything about it in this for this course. Okay, so we'll start from the simplest case, and this case is molecular lattices. What do we know about molecular lattices? Well, the basic thing we know about molecular lattices is that they are weakly bound. Molecules, when we are saying molecular lattices, the molecules themselves have no charge, they are neutral. What do I mean have no charge? The number of electrons and the number of protons in these molecules or atoms or whatever are equal, therefore there's no direct Coulomb interactions between these atoms. Okay, so nothing keeps them together. Well, it's not as simple as that. To first order, although these atoms, for simplicity, I'll call them atoms, although they can be molecules, are neutral. If they're neutral, there's no, as I said, Coulomb interaction. What can we expect even in a neutral atom? What kind of electromagnetic interaction? Excuse me? Let's not skip three. First, we will end up that this is the cause of the van der Waals force, but before that, why should there be at all any it's an electromagnetic attraction.
Magnetic force on the movement of the
magnetic forces are much, much, much weaker than the force we are talking about. Dipoles. What do I mean by dipoles? The fact that you have overall neutral configuration doesn't mean that there can't somehow arise a separation between the negative and the positive charge, meaning that we have a dipole moment. So we assume that the interaction between those atoms is dipole interactions. Okay, so for just as a cartoon, we have here the positive center of charge. As I said, I'm talking about atoms, so that's just the nucleus. And we have a negative charge because of the electrons. And when we average the position of all the electrons at a given time, we can get an average center of charge, which is not exactly on the nucleus, meaning that we have here an electric dipole. Okay. We have here the next neighbor, and here this dipole can point in some other direction. Can try. Okay, so the only thing here that's important is the dipole itself, so I write P1 and P2.
Why are there two minuses in the P1? Is that a mistake?
The minus, it's a smudge. Okay, so we have two dipole moments. Of course, in a lattice we have as many as dipole moments as we have lattice points. Okay, what do we need to know about the electric field of a dipole? The first thing that we should know is that the electric field is proportional so two things are important here. It dies out much quicker than a Coulomb field. It doesn't die as 1 over r, it dies as 1 over r to the cube. And it has also some dependence on the direction. In general, I can write that the electromagnetic interaction, or the energy, would be proportional to P1 Okay, so it depends very strongly on the distance. It's effective at short distances, but dies out quite quickly as we go further on. So now we're almost at van der Waals force. Okay, van der Waals force. Or just a moment.
למה הכפלת בעצם את האנרגיה שלהם ולא נגיד חיברת של כל אחד מה...
Because basically energy is a field square. please pay attention. We're doing here very hand waving. If I would go back to your second year and do electromagnetic, honest to God, electromagnetic calculation, we'll have to take into account the angles between the dipoles and so on and so forth. It's quite a complicated field. We are trying to get a feel how does this potential generally look? And in a moment you'll see that we'll add another term that must be there that we'll pull out of thin air. And although we pulled it out of thin air, we'll see towards the end of this lecture that we can actually measure and give a good estimation what is its strength. So we are modeling and doing the simplest models that we can. Don't care much about details. You'll see further on that a lot of physics I can pull out without knowing all the minute microscopical details of the model. If you have a bit of experience in thermodynamics, you'll see you are already aware that a lot of the properties of the bulk of macroscopical bodies, you don't really need to have all the details. They don't play an important role there. Okay, so the Lennard-Jones potential, and tomorrow I'll have a very unusual lecture because this guy, Leonard, is a very, I'm hesitating between interesting and despicable physicist that is very deeply connected to the Holocaust, and I'll talk about it tomorrow, just one day before the Holocaust day, but and he's not a minor physicist. This guy has received the Nobel Prize. And the potential that these two guys proposed, actually each one separately, but more or less in the same time, so it's called the Lennard-Jones potential, is the following potential. Here, of course, I forgot the minus, important. So, why this potential? Okay, this part we gave somewhat of an explanation. That's the interactions, the attraction between dipole moments. So, if I'm plotting the potential as function of r, okay, so what's bad with this? Why did I add another term, or not I? These two gentlemen?
Have some kind of background.
If I'm looking only on this potential, life is good, but doesn't describe real life. Meaning, it's very easy to find the minimum. The minimum, all of them clumped together at zero, no lattice, no spatial structure. Life is on one hand simple, but on the other hand certainly not good. Okay, so just think about it. I have two atoms. They attract each other. So they move closer, 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 closer. At some point, they'll start to repel each other because of the outside cloud of electrons. Okay, so how do they model this potential? Okay, repel, meaning it has to be positive. It has to be shorter range than this guy's, otherwise the repulsion will send it to infinity again. Not a good description. Why 12? Mathematical convenience. Because r to the 6 squared is just r to the 12. Could it be something else? Yes. Anything larger than 6. Could we measure it? Yes. We can do a measurement and more or less extract what is the appropriate power here. Comes out something in between 8, 9, 10, 12, depending on the constituents of the lattice. But as a first step, this model has all that we need in order to get some feeling what is the energy that keeps this lattice together. So, sorry, this guy doesn't go negative, it falls off here, so this is BR to the 12, and you can see that if we combine them both together, we get something with a minimum, which is what we expect from a lattice. That's the reason that we have a lattice point, because there's some distance between the atom that is the best energetically, and when we go to low temperatures, it sits there. Why don't I care about high temperatures?
Because it's a gas.
Right, it doesn't remain, no lattice remains at high enough temperatures. Okay, so we have everything that we need in order to perform a calculation. Just
איך אנחנו יודעים שהתנהגות היא 4 בחזקת 12, 1 בחזקת 12?
I told you, we don't. The only thing we know that the power here has to be larger than 6. 12 we chose because it's convenient mathematically. We'll do the calculation, get results, and after that we'll see how we can extract this power from measurement, and I'll give you some data about what is actually measured. Just we have here two parameters. Some people don't work with A and B, they work with epsilon and sigma. Doesn't make a difference, it's just, in some sense, more convenient. So sigma and epsilon is A to the square 4b. So sigma is units of length, and epsilon is units of energy. Why did we do it? On one hand, instead of having two constants with different units, we have now two within here clear units. What is in play here? Sigma is the distance, epsilon is the energy. Okay. What is the energy of the whole lattice? Writing it down is very simple. U is the energy of the lattice. Sum up over all the pairs. Between each pair there is this interaction. Sum up over all the pairs. You get the energy in the lattice. I didn't say that the summation is easy, but writing it down is very easy. And transparent, it's clear what we are doing here.
Don't we need to define something like nearest neighbors to do that summation?
No. That's R is all the points in the lattice, right? Starting from where? Starting from wherever you choose, right? So I'm choosing one and summing over all the pairs. You can logically claim that far away large R's will contribute less than nearest neighbors. But in general, as long as we're dealing with pairwise interactions, and all basic interactions that we have in physics are pairwise, this is correct. I didn't say it's easy to calculate, but correct? Clearly. The only thing that I forgot here is half, because I'm counting pairs. So if I'm counting what's between 1 and 2, it's also between 2 and 1, and I shouldn't count it twice. Yes?
Do we, what was my question again? Okay, do we only calculate the two nearest guy?
R is all the in the case of a three-dimensional lattice, I have an infinite number of neighbors.
So even if he's not the closest one, he's still considered somewhere, even if they sound if before him?
As I said, I don't, at the moment I wrote the most general term. Now I'm going to calculate it. The point is, with a potential that becomes very small very quick, summing up is not a problem. We'll see that we'll run into extreme problems when instead of the molecular lattice, where it falls off like 1 over r to the 6, we'll take the simple case of the ionic lattice where it falls off like 1 over r. Their life is bad because there you have to take all of them into account. Okay, so the answer is So what did I do here? Basically, I threw everything complicated into this function. But this is a mathematical problem. It will give us a number. Just I'm going, tell me what's the lattice you're interested in. Go sum up this number to the 6th for here, this number to the 12th for here, and you'll get a number. Okay, it's a problem of counting. And as you see, if you're lazy and count only 2, 3 nearest concentric shells of neighbors, you're more or less quite exact because it goes down very quickly. Good. So, in case you're really a number nuts, I'll write you down these A's for a few examples of lattices. SC simple cubic, BCC, and FCC. And if you want to recheck my numbers, open Ashcroft. I think chapter 19 or 20, you'll have the table. Okay. At the end of the day, all we need to know it's a number of order 10. That's the important thing. Okay. How do I find the distance in units of sigma for the lattice? Any idea?
What's the meaning of distance in this case? The distance between the atoms?
What?
But there can be different distances between different atoms.
So the distance between nearest neighbors. So how do I find it?
With the algorithms we showed last lecture, right? With all the
No, I don't want to do here measurement. I want to pull it out from the expression of energy.
We can see what expression gives us a minimum.
Exactly, I'll find the minimum of energy. Because as I move the temperature to lower and lower temperatures, I expect to see the lattice closer and closer to minimum. At 0 temperature, 0 Kelvin of course, I expect to have it exactly at minimum. This is just an expression which carries what I said in words. Okay, so I take the expression there and okay. And that's the reason why I chose power of 12. Gives a nice ratio. Okay, so without knowing almost anything about the lattice structure, these guys are up and are 1/6. 1/6 of two numbers that the ratio between them is the order of 2 is a very close to 1. And that's in general the result. Sigma is very close, R0 is very close to sigma. So sigma gives us the scale of the lattice. So if it's
Is
there,
sigma also under the square root? Under the shit?
no, it can't be just units. This is unitless. This is length, so that's okay. One thing that is a general problem that doesn't matter how much you hammer it down in students, you come to an exam and find something that you tear your hair out, look at the units. You got a result, look at the units. That's the easiest, fastest way to check if at least you got something that makes sense. If I add here units of I don't know what, distance cube, I did a mistake. But as long as I have the same units, maybe I did a mistake here, but does it really change much? No. Okay, so for simple cubic, it's what? R0 is 1.07, but it's not very important, these numbers. Again, if you're very interested, check up Ashcroft, but it's almost 1 for all lattice structures that we know. Okay, so basically now I can say even what is the energy of the whole lattice.
So we're using sigma both as units and as a variable here?
We define sigma somewhere as a ratio of the two numbers that defines the van der Waals potential. So it has a number and it has units. So that's all.
So it has units of sigma and it is also...
No, sigma is units of length. I think I convinced you when I wrote that. You add some constant over r to the 6, some other constant which was r to the 12. You divide it by something, it's to the 6, and you pull out the sixth root, and it's units of length. Nothing magical here. Okay, so what's the energy? Just go back. Enter instead of R0, and you get the result. Okay, so it's just substituting R with the values that we got here. And not surprising, the energy depends on epsilon, which is the units of energy, times some numerical factor that depends on the lattice type. For simple cubic, it's minus 5, 7. Okay. Why is this interesting? Because this we can approach through experiment. We can do an experiment which pulls out something that is connected to this energy. And this is the bulk modulus. What is the bulk modulus? Okay, I see some of you are getting flashbacks, if not to say nightmares from thermodynamics, where you had whole tables of do something to do something else is equal something else. But that's the only thing I'm introducing in this lecture. And let's try to understand what's written here. Well, P, pressure. V, volume. T, temperature. Okay, so at least we know what are the letters appearing in this definition. So what do we do here? We go and change the volume and see what happens to the pressure. In simple layman term, what do I do?
Expand the tank and measure.
To expand, it's a bit difficult. What's easier?
Compress.
Press. We press this lattice, this piece of solid. See what happens to the volume as we press it. Makes sense in some, if we think about it a bit. We want to see what happens to the energy. Let's try to squeeze it together and see what happens. Why at t equals 0? Because we are looking at the minimum. So if the lattice is more or less doesn't expand much as function of temperature, we can do it easily at higher temperatures. If it's very sensitive, we should do it as close to the absolute 0 as possible. Okay, so if we sweep aside all our anxieties about thermodynamics, it's very clear what we are doing here. We squeeze and we see how much it resists to this squeezing. Makes sense. Okay, so now we're stuck only with doing the mathematics. Pressure we don't know here. pressure is just minus the change in the energy by changing the volume. Last thermodynamical connections that we're using here, again, intuitively very understandable. What is force? The change in energy, minus. Somewhere in 11th grade, we ran into it. So, same thing. Okay, here we have everything. We have the volume, we have the energy, so now it becomes mathematics. So, are you we calculated it for 1 point. Okay, so the small u that we calculate is just the general energy of the system divided by n, the number of lattice points or number of molecules, atoms, whatever. Curly V is the volume of one atom. Makes sense. Now, the volume dependence on R on the distance to the nearest neighbor depends on the lattice. Let's choose one lattice. It doesn't matter. Let's choose FCC. Any other lattice would be R to the cube with some other number here. Doesn't really change the calculation. Simple cubic, it will be just R to the third. Okay, so now we know U will exchange the energy with the energy per particle. So we know U. We almost know V. We know V as dependence on R, but also U we know as dependence on R. So instead of we will exchange dot to V by the chain rule. Just the chain rule. So if I take the definition of B, someone can tell me how can I convince myself immediately that I didn't miss here any factors of n? I changed it from large U and large V to small u and small v. because it cancels out, we can see 1 up, 1 down, 1 up, 1 down, no factors of n, no mistake. Okay. Well, I erased u, but u we know. Okay, so now we replace the dependence on me, on b or me, whatever you want to call it, with this, and perform the derivative, and we get, let's do it step by step. Okay? I'm not looking on the numerical factors, just the important stuff, the powers of r. Okay, we have 1 over r squared here, because of this. We should have 1 over r squared here, but the volume per particle also depends on r to the third, so it's r here. So up to constant, we're okay. Put in constants and hopefully we're also okay. Okay, so we have B. Okay, so I'm looking somewhere close to the minimum, close to equilibrium. So I should perform the derivative twice, put in R0, and I'll get so perform it at home, check if I'm correct. If not, go and consult Ashcroft. And we end up is this result reasonable? 25, I can't tell you. But look at this. Energy, no volume, 1 over volume. Energy per volume. Energy per volume. Okay. So maybe I did mistakes with the constant, but I certainly got at least the correct units. Okay. So What does it give me? Basically, gives me a way, if I pull out sigma out of measurements like X-ray measurements that give me the structure of the lattice. So there I can know the right numbers for my lattice. I can pull out here epsilon from this measurement. Okay, so let's do very similar. It's most of the way similar to what we did for this molecular lattices for ions. Okay. Finished with this? Sure.
Find sigma by d over a power of the not 6. But and the sigma is directly connected to R0. But R0 is supposed to be connected to the temperature. It has to be
No. When we're saying it's at minimum energy, the T goes to 0. If you remember the definition of the bulk modulus, there appear T equals 0. Said that if it doesn't expand much as function of temperature at low temperatures, you can fudge it and go to somewhat higher temperatures. But it is the case where we're looking at 0 temperature. Why can't we do anything more at the moment? For the simple reason. Once you have things that start to vibrate, what do we have? Elastic modes. Think about springs that start to move. You'll start to have some elastic modes. We didn't have yet formalized elastic modes. We'll get there. Apparently not in this lecture, but in the next one. Okay, so we are looking now at so I'm drawing the simplest ionic lattice. Okay. What's the first thing that I can say about this lattice, about expressing it as lattice points?
That it isn't a lattice.
It's not a lattice.
Two lattices.
It's composed of a lattice which has 2 atoms per unit cell. Okay, fine. But it's just something that we should keep in mind. So instead of this structure, we're actually in 2 dimensions looking at this structure, 3 dimensions. Use your imagination. Okay. So basically, we'll have here an FCC lattice, because you see that layer above it will be moved. So it's an FCC lattice. Where we have, let's choose a negative ion at R. And at R plus we have a positive. And instead of writing this whole thing, we sometimes just say D. Okay. So, how does U look like? Again, this lattice is not stable. Will crunch down. Every plus will stick to the minus, and that's that. Why doesn't it? Again, I have to put in some repulsion. So we have something that depends on the Coulombic interaction between them. And some part that depends on the repulsion. Okay? The same things that we did before. Now, just for brevity, I'll first consider the Coulombic part. And going back exactly to what we did previously, so what do I have here? Unlike the previous case, I do have interaction with its partner from the same lattice cell. They too attract each other. Meaning that the further on, more energy. That's why it's plus. Then it interacts with all pairs in the other lattice points. Attractive with the opposite sign. You don't need plus minus. This is minus. Repulsion with the guy. And here, life is good. I know exactly the energy of a pair. Minus E squared over R. Okay, this seems, now sum up these series and you'll have here a number. Which is what we'll do, but I'll caution that this summation is fraught with mathematical problems because series of 1 over r diverge. Here the situation is a bit better because you have plus and minus signs, but it tells you that you should approach it with a lot, being very careful. And I won't go into the details. I'll just point you. Guy Hewlett did it carefully. I think it's a W, not a U. And he got a number. That's the only important thing. My point is if you do it in a different way, you can come up here with a different number, and he tried to get something close to experiment. So unlike mathematicians, for a physicist, at least at the end, you can compare it to something. Something that happens on and on in physics. Our best theory, our most exact theory, QED, for quantum field, quantum electrodynamics field theory, if you go and perform a naive summations there, you get divergence.
Shouldn't you then renormalize the results by measurement?
Exactly. Yeah. So I'm pointing that this is a more simple case of such behavior. Well, at least if you go to consult with a real mathematician, will throw you out of the window and say you don't have here a mathematically consistent theory. But it works. Okay, so same as previously. Again, I have to have here the repulsion, so I'm writing C over R to the power of n. Why here am I so blasé and take any n, and previously I insisted on 12?
That it depends on the lattice.
No, because here I have power of 1, so everything is a multiplication of 1. Previously I had 6, so I wanted some simple multiplication of 6, which is simplest is 12. So that's the only reason. But you'll see how here, so math doesn't become more complicated if I choose any integer n here. Okay. So what do I do? The same, exactly the same games that I did before. First of all, find where it's minimum. the minimum of this energy. Again, I don't go through all the details. Derivative equal 0, and we get the value of R0. We can get the value of the energy at zero temperature or at equilibrium. And if I prefer the bulk modulo, and if I go to the measurement, alpha is the summation, R0 is a result of this calculation, so I can actually, by measurement of B, extract N. And for most lattices that ionic lattices, we know M is between 6 and 10. Okay, so we are consistent. Good. What can we do about the case where we have covalent or metallic bonds? I'll defer it as homework. No, that's a joke. I'll defer to a PhD project, and that's serious. Calculating the energies of a certain lattice. In these cases, you have to go and do quite cumbersome and resource consuming numerical calculations in order to say something about the energy of the lattice. If you think about it, basically, if we really could do any calculation, we could say, someone could come to us and say, okay, I want to build a material out of this number of type A atoms, this number of type B atoms, this number of type C atoms, calculate what will be the lattice structure and what will be the bonding energies there. And today it's still easier to go to the lab, cook it up and see what you get than calculate it from first principle, although with time we are getting better at estimating it. Okay, so that's about what we can do in calculating energies of these Okay. Unfortunately, from the point of view of doing calculations, fortunately, out of the point of view of living, we don't live in t equals 0. So, a lattice at finite temperature, let's say at room temperature, atoms are not necessarily in the lattice points. Okay. Nevertheless, the mere fact that we have lattices tells us that they can't be very far from the lattice points. If they are very far from the lattice points, it's not a lattice anymore, it's either a liquid or gas, but certainly not a solid. So, at some temperature range, the atoms are around the lattice point, but not exactly at the lattice point. Why are they around the lattice points? Why don't they go and take a hike, go anywhere they want? Because it's the minimum energy, and apparently they're stuck in a potential well which confines them more or less to the vicinity of the lattice point. Otherwise, they won't be there. Okay, let's try to write a theory to understand how far are they moving out of the lattice points. So we will be eventually introduced to a new quantum particle known as phonons. Okay. To what does it sound like?
Photons.
Photons. Actually, they are cousins. Photons are the quantization of the electric field. Phonons are the quantization of the acoustic field, the acoustic waves within the soul. So we'll first have to understand what are the acoustic waves in solids, the same way that we learned how to treat electromagnetic waves in the classical case, and then we'll see how to quantize them. Well, you didn't really see how to quantize the electromagnetic fields, unless I'm seriously mistaken.
We didn't learn QED, if that's what you mean.
No, even before just the concept. You are right. When you start in your second degree, take advanced quantum mechanics, we won't start by quantizing electromagnetic fields. We'll start by quantizing the phonons. Why? They're much simpler. Why? Because we don't have two fields E and B. They don't necessarily, we'll see when yes and when no, they don't have polarization. They don't have polarization that stands perpendicular to the direction of propagation, so they are a lot simpler. So that's the reason why most courses that do field theory, quantization of field theory, start with phonons, not with electromagnetic waves. Nevertheless, both phonons and photons have the same phasor, physically speaking. Einstein. He came with the concept of photons, and he came with the concept of phonons. And again, in a typical Einsteinian way, he decided that there must be quantized phonons, acoustical waves in solids, from a simple experiment. Where did he actually really corroborate the ideas that you have a photon as a physical entity?
The photoelectric effect.
The photoelectric effect. Phonons, then we're going back to thermodynamics, because treating solid state objects are usually some kind of thermodynamical measurement. Heat capacity. How much energy can you put into a system to change temperature? Or vice versa, how much and sounds scary, but it's very simple, at least to show that the classical picture can't be true in solids was very easy, and the explanation Einstein gave is those phonons, again, quantization. Okay, so let's do the first couple of very simple steps, and the first one would be, what is the energy of the lattice? Okay, we did it actually. U. Remember previously we did small u, the energy per lattice point. The overall energy of the lattice whatever the potential between those points, that for a ionic and for a molecular lattice we calculated, for a covalent we don't know. But there is some potential between each 2 points. Okay, here I'm taking both points, so I'm doing the total energy. I could go back to what I did before and just go and sum over 1 point and multiply by n over 2. It's fine. Why do I need to write it this way? Because now this is in the case that all the atoms sit at lattice points. Okay. If all of them sit at lattice points, this transition is okay. Because all lattice points are equivalent, so I just can multiply by n. R minus R prime is again a lattice vector. All of them are identical. Life is good. If they move, I have to use this definition. Because now, instead of that all of them are in lattice points. All the atoms that are at some point are an N prime. Well, this is very general. This is always true. Solid, liquid, gas, no difference. Where do I keep the fact that these atoms are still in a lattice? In the assumption that R is the lattice point plus some small deviation U from the lattice point, which is small. Small compared to what? Small compared to the distance between the lattice points. So I'm going to each lattice point and asking, okay, tell me please, the atom, where is it really here? Well, so it's moved by some direction and size from the lattice point. This is this U. For each lattice point, it could be different. For all of them move in unanimously. So simple transition of the lattice and nothing changes. And what we'll do in the next lecture, we'll take this, go back to here, assume that U is small, and try to solve it. And how we will solve it? Small Taylor expansion. And Taylor expansion makes sense because around equilibrium, we know that we can do a Taylor expansion. Okay, so that's for the next lecture.
Thank you.